nearer to this, I have these points, right? These points. Fine. These are my nearer points to the orange star. Yeah. So this will, get clustered in with this centroid. Okay. So we have this orange, and here we have this orange star, and similarly the yellow clusters are being formed. Okay. So this process repeats until the convergence, until there is no particular movement or something. Fine. See, what happens is when I am grouping my clusters, what happens is after calculating distance from each point, centroid from each point, what happens is we calculate the mean distance. Okay, we calculate the mean distance of this centroid and we shift it. Fine. So as you can see, the centroid was first over here, and this has got shifted a bit this side. Why? Because these points are nearer to it. So these are similar points. Okay. Similarly, the yellow point has been shifted over here. Okay, and I've got yellow points over here, orange points over here. A bit of yellow points are here because this distance is least than this distance. Fine. So we'll be basically repeating this step until we don't have a significant movement or something. Fine. And this is how my clusters are formed. Okay, this is how my clusters are formed. Fine. I hope you understand this thing. So what happens is, first what we do is we select the value of k. Fine. Then the point nearest to the centroid, we basically group them. Okay. Then we move the centroids by calculating the mean distance, and we repeat this process till the convergence. This is how the k-means algorithm works. It's a simple algorithm. It's very simple. Okay. This is how the k-means algorithm works. Fine. Okay. Yeah. Yeah, so let's go. Yes. Again, this is the same intuition which is written over here. Yeah. So we have random clusters. Fine. Random points. We initialize some clusters. Fine. Then what we do is, okay, now the distance parameter. See, the distance parameter is basically the Euclidean distance. Okay. So Euclidean distance, I hope you're aware of Euclidean distance from the previous session. That is under root of x2 minus x1 whole square plus y2 minus y1 whole square. As this is 2D, so this will basically form a Pythagoras theorem or something. Okay, see, as we use the, what we have, just a second. Oh, slides are not changing. Okay, they are changing. Okay, fine. Guys, you can speak, like you can just on your mics and tell me, interrupt me, fine? Or else, I have to again change that windows. Okay, let's continue. So what happens is, random clusters are formed by updating the centroid positions. Fine. And here we have a cluster till the convergence. Repeat this procedure till the convergence. Okay, see, so I have my blue cluster, then I have my here orange one, and then the green one. Okay. Now, what is k-means plus plus? Okay, before this k-means plus plus, I would like to discuss about how do you select the value of k. Fine. How do you select the value of k? Okay. Yeah. Okay, let's discuss the k-means plus plus part itself before. So what happens in So what happens in k-means plus plus is sometimes our clusters are basically they are formed in a wrong manner. See, just see this example. We have this set of data points over here, then we have another data point here and here. So it's clearly seen that we'll be basically having 3 clusters over here: the red, green, and blue. Fine. But what happens in k-means is, if you initialize k-means just like that, what happens sometimes is the 2 centroids will basically form in this set of data points instead of forming here and here, and a single data point will be formed over here. Okay, let me repeat it again. Why the concept of k-means came because k-means plus plus came because when we are randomly initializing our centroids through k-means, sometimes we get the wrong set of centroids and clusters. Okay, the expected set of centroids are towards your left side, that is the red, green and blue over here. But what happens sometimes is we will get two centroids in the same cluster, and we'll get just a single centroid over here, so they are wrongly placed. Fine. So what is this reason? Like, what's the reason of this to be happen? The reason is we are initializing the clusters, the centroids very closely. Okay, the if you can see the centroids over here, these three centroids, they are placed very nearly. Okay, so this should not happen. Fine, we should initialize the centroids a bit of far away. That's what k-means plus plus does. Fine, it's just a small change in a Python code, and with the help of that you can basically initialize the k-means plus plus. Fine. So this is k-means plus plus. This is basically to avoid the random initialization trap. This is called the random initialization trap. The slide hasn't changed. Well, actually I didn't change any slide. Okay, Karthik. It's fine. Okay, everyone, did you understand till here? If you want, I can repeat it again. Is it clear? Ragmay, Sujit, Shrikant, Likit, everyone, Mohit? Yeah. You want me to repeat it again? Okay, it's clear. Fine. So, till now, what we have studied why we use the unsupervised machine learning part. Fine. Then we discussed the first algorithm, that is the k-means algorithm. Fine. The intuition behind the k-means algorithm. What is the distance parameter used in k-means algorithm? That's the Euclidean distance. See, sometimes we even use a distance parameter called the Manhattan distance. Okay, that's nothing but mod of x2 minus x1 plus mod of y2 minus y1. That's it. Okay, that's the Manhattan distance parameter. Okay, but it is recommended to use Euclidean distance itself. Is it clear? Fine. Then we went to this wrong clustering. The centroids and the clusters are basically placed in a wrong manner. So this entire thing is basically called as random initialization trap. Okay. So if anyone asks you what is random initialization trap, then you're going to simply tell that during the k-means algorithm, when it works, sometimes the centroids and the clusters are placed in a wrong manner. That's it. Okay. And for that, we have k-means plus plus. Fine. Okay. Now let's come to the next part, that is how do we select the value of k. So let's see this part. Fine. So there's something called as elbow method. Okay, there's something called as elbow method. Fine. What elbow method does is, like you can imagine a random cluster. Okay, you can basically imagine a random cluster like let me just share this thing with you like this. Here. Okay, see, how do we decide the value of k? Okay, so there's something called as WCSS. Okay, WCSS. What is the full form of WCSS? Within cluster sum of squares. Okay, within cluster sum of squares. Okay, so what happens is, let's say this is my axis. Okay, this is my thing. Okay, and I'm pointing some random data points over here. Okay, fine. These are my random data points. Okay, in the cluster. What I'm doing is I'm choosing a random point. Fine, I'm choosing a random point over here. 1 second. Yeah, I'm choosing a random point over here. Say, okay, Now what I'm doing is I'll be iterating to the with the value of k. Let's say I have k equal to 1. So what I'm doing is I'm taking one centroid. From that one centroid, what I am doing is I am calculating the distance of each point from that cluster centroid. Okay, I'm calculating this distance. Okay, and basically calculating this distance. Fine. So distance between the points to the nearest to the centroid. Okay, and I'm squaring them. So this is my WCSS basically. What I'm doing is I will take the distance. Fine. I'll add them and I'll square them. Fine. So this is my WCSS for k equal to 1. Let's say I'm taking k equal to 2. Fine. If I'm taking k equal to 2, this is my axis. Fine. These are our points. Okay. These are my points. Let's say 3 points only here. Okay. Fine. These are my points. Okay. Now, first we are taking k equal to 1. So 1 centroid. Now what I am doing is I'm taking k equal to 2. That means I'm initializing 2 centroids. Right? I'm initializing 2 centroids. Fine. So what I will do is, first, let's say this centroid is a part of this cluster, and this centroid is part of this cluster. So what will I do is I will, from this centroid, okay, from this centroid, I will calculate the distance of this point, these points, as these points are the part of the same cluster. Fine. As these points are the part of same cluster. So this is cluster 1. And now I'm calculating the distance of these points from centroid 2. Fine. From centroid 2. Okay. And after adding, what should I do? I should square them. So basically I'm getting this and this. Fine. So if you compare this scenario and this scenario, my WCSS value will reduce as the distance will be shortened, right? As the distance will be shortened. Fine. So if you see the value of my WCSS, it will be gradually decreasing. Fine. The value will be gradually decreasing. And that value, okay, that curve which you get of WCSS, is it visible? Is it visible? Yeah, cool. So after taking iterating through the values of k from 1, 2, 3, 4, and so on, if you see the curve comes something like this. Okay, this is my curve. This curve is known as an elbow curve. Fine. This is an elbow curve. So the method to calculate the value of k is the elbow curve method. What we do is we take the value of k from one and just iterate it, and we calculate the WCSS. What is the WCSS? It is the sum of the square of distance between the points to nearer to the centroid in a particular cluster. Fine. Now, as you can see, there is a point of inflection over here, right? After k equal to 3. Let's number of clusters, I have 3. So after this, we can see that there's a point of inflection over here. So the value of k which I have to take is 3, because here is the point of inflection. That's why I have formed 3 clusters over here. If you see this example, 3 clusters are formed. So this is how we take the value of k. Okay, is this clear? This is how we take the value of k. Okay, so these are the steps. You can just go through it. I'm not just going to simply read the PPTs. Okay, fine. This is just for your reference. Okay, this is the distance parameter, how we take it. Fine. Okay, is it clear until here, guys? Is it clear? Okay, great. Fine. So we have discussed the mathematical intuition, and then we discussed the random initialization trap, and then finally we discussed how do we calculate the value of k. Fine. Okay. So now we'll be moving towards the second algorithm. Fine. That is the hierarchical clustering. Okay. Okay. Before moving forward, does any one of you have any prior knowledge of machine learning before, or this is the first time you're studying? Like, how many of you are studying it first time, and how many of you have studied before? Respond in the chat box. It's fine. First time. Okay. Okay. What about others? Sujit, Karthik. I have basic knowledge. First time Mohit. Likit. Kumaran. Basics. First time. Okay. Okay. Fine. Yeah. So, see, I'll be taking the practical implementation after some time together of both hierarchical clustering as well as the k-means clustering, because see, the code is totally similar. Fine. There's no change in the code. There's just 3 to 4 lines of changing, and that's it. We are done with the clustering part. It's very simple. Okay. Again, we don't need to memorize those codes. Fine. What basically everyone does is just refer the documentation. If you have doubt, just refer the documentation, take that code snippet and do the changes according to yourself. Okay, we are not coders. Okay, we have another work regarding apart from coding. Fine, you should have a basic knowledge, but yeah, if you have any confusion, just go and refer to the scikit-learn documentation, or even if you have any doubt in the pandas code or somewhere, just refer the documentation. There's no shame in that. Fine. Okay. Keeping this aside, let's go to the hierarchical clustering part. Now, what is hierarchical clustering? See, again, this is just the PPT. Okay, let me first discuss it with the PPT. So what happens in hierarchical clustering is, I hope it's visible. Yeah, it is visible. Yeah. What happens in hierarchical clustering is, let's say we have these 6 points, okay? These 6 points. First, what we will do is, we will initially consider each point as a separate cluster, okay? So basically we're initializing 6 centroids over here, as you can see. Okay, we are initializing here 6 centroids. Fine, these 3 and these 3. Okay, now find the nearest point and create a new cluster, basically. Fine. Now if you see in this figure 2, orange and purple, these 2 are close. So what I'm doing is I'm forming one cluster as these 2 are close. Again, the distance parameter will be Euclidean distance. Okay, the distance parameter will be Euclidean distance. So what happens here is, the orange point and the purple point, they combine and form a cluster. Okay, then next what happens is, this red point and this blue point, they are closer, so they form another cluster over here. So we have 2 clusters. Fine. Now closer to these this red cluster, we have this green point, and closer to this orange cluster, we have this another point, the yellow point. Okay, so what happens is, this forms one cluster and this forms another cluster. At the end, these 2 clusters, they form a entire one cluster. So this is the procedure of how the hierarchical clustering algorithm works. Basically, where we are initializing each point as a centroid, and at the end we are basically forming one cluster. Fine, we'll be repeating this step and we'll be forming one cluster. Okay, but now the question arises, how do we get to know that how many clusters are basically there in my particular data points? Let's say last time we had those 3 points. So how will I get to know my number of clusters? Okay, that's the question, right? So the answer to this question is dendrograms. Dendrograms basically help you to find the number of clusters in your data points. Okay, how many clusters you need to initialize, basically. Okay, so for dendrograms, I'll show this diagram. Okay, yeah. Okay, visible? Is it visible? Okay. So okay, the intuition is clear, right? What we are basically doing in hierarchical clustering. Is it clear, right? Is it clear? Great. Okay. So now let's go to the clustering part. Where was it? Yeah. Okay. So what I'm doing is, let's take the circle. See, point 1 and point 2 are basically closer to each other. Let's say they are closer to each other. So what I'm doing is I'm forming them as one cluster. Okay. So this is my first cluster. Okay. Then I can see here point 4 and point 5 are basically closer to each other. So basically they form another cluster. Before this, what happens is everyone are a single centroid. So basically I have for 6 centroids, okay? And then the clusters are forming, okay? Now P1 and P2 are one cluster, okay? Closer to this cluster, I have my point 3. So what I'm doing is I'm making this as one cluster, yeah? And now closer to point 4 and point 5 cluster, I have point 6. So I'm making this as one cluster. Fine. And then these two clusters, the gray one and the green one, okay, they'll form one big cluster just like this. Okay, just ignore the drawing. Okay, they'll form one big cluster just like this. Okay, so how will I get to my how will I get to know my number of cluster? See, so these are something this picture over here, these are basically called your dendrograms. How do you draw a dendrogram? See, look at this axis. So this is my points and this is my Euclidean distance, basically the y-axis, and these are my centroids. Okay, so as you can see, yeah, I had first my point 1 and it got combined with point 2 and formed one cluster. Okay, then what happened was I had point 4 and I had point 5, they formed another cluster. Okay, so I got these two like these lines. Okay, then what happened was these two clusters, okay, this one cluster of point 1 and point 2, they were combined with 3. So I formed this line, the square, whatever, the rectangles basically. Okay, the point 4 and the point 5 cluster were combined with 6. So I've got this, and at the last, this cluster and this cluster were combined to form one cluster. Okay, so now how should I decide my number of clusters basically in the entire data point, like how many classes basically? So what you do is draw a horizontal line. Okay, draw a horizontal line through each vertical line and just check. Okay, just check, is there any horizontal line passing through it? What does this mean is, let's say I'm taking this longest, you have to select the longest vertical line. Let us say I'm selecting this as my longest vertical line. Okay, and I'm selecting this as my longest vertical line. So what will I do is I will pass a line. Okay, now as you can see, this portion, okay, as you can see, this portion is a horizontal line over here, right, of this cluster. So I will not select this point. Okay, so you have to basically select the longest vertical line where there's no horizontal line passing through it. Okay, well, if you see, this is the longest vertical line, right, but this was a bit short. I drew it a bit wrong. The main crux is that if you see, this is my vertical line. Okay, this is my vertical line. If I pass a line through it, if you see, there's no horizontal line passing through it, right? There's no horizontal line passing through it. Let's say if you take this line, okay, and if you cut it, fine, this is one line passing, right? This is one line passing, right? This. Okay, so this is how I select my number of clusters. Now if I drew this horizontal line, you can see that there are two vertical lines cutting it where there's no other horizontal line, right? So there are two vertical lines, so I have my two clusters. Fine, this cluster and this cluster as it touching over here. Okay, is this clear, or should I repeat it again? Everyone, is it clear? Okay. See, if you have any doubts, just tell me. I'll repeat it again. Okay. All right. Now, so this is the algorithm. That's it. There's nothing. There's nothing in, guys. There's nothing in unsupervised learning. Basically, fine. I mean, if you understand the algorithms, each and every machine learning algorithms, to be honest, there's nothing tough in understanding those algorithms, right? Fine. So this was your k-means clustering and hierarchical clustering. Okay, this was your k-means clustering and hierarchical clustering. There's one more thing over here now. See, like we had the evaluation metrics, right? If you recall the regression part, we had our evaluation metrics that r2 r squared, right? You guys remember it, right? The regression part, evaluation metrics was the r squared, right? Yeah. And if you come to the classification part, we had our precision, recall, then F1 score, right? So similarly, we have an evaluation metrics for unsupervised machine learning also, the clustering part. That is something called as silhouette score. Okay, silhouette score is one evaluation metrics by which you can say, yeah, let's say this is my clustering. Is this clustering a good clustering or a bad clustering? Fine. So that thing will be told by silhouette score. Okay, silhouette score. Now you can refer the online papers or something, but I have written a short description of it. Yeah, I've written a short description of silhouette score. This is okay. So is it visible? Is it visible? Yeah. Okay. Okay. So we discussed k-means, we discussed the hierarchical clustering part. Now we are coming towards the silhouette score, which is the evaluation metrics for these algorithms. Now what happens is, basically, this is the formula of silhouette score. S of I is equals to B of I minus A of I divided by max of A of I comma B of I. Okay. Now what is A of I and what is B of I? Fine. What is A of I and what is B of I? So A of I is basically, see, A of I is, let's say this is my one cluster, okay, formed. Okay, let's just focus on AI part. Okay, A of I. Let's say this is my cluster. What will I do is, I will take a random point, okay, and I'll calculate the distances of the other points from this point. Okay, fine. I'll calculate the distance, okay, and find the average of the summation. Okay, is it clear? Is this step clear? Okay, this is A of I. Is this clear, guys? Okay, great, fine. So this was A of I. Now let's go to B of I. Okay, we have got A of I. So what I'm basically doing is summation of one point to all the other points. Okay, and after the summation, I'm taking the average. Fine. Now B of I. What is B of I? B of I is basically, we basically find the mean dissimilarity of the point I. Okay, mean dissimilarity. What is mean dissimilarity? Okay, so see, this was the first cluster. Okay, we had taken a random point and we had found the summation and then the average of those points, right? Now I'm taking another cluster over here. Okay, let's say this is the cluster. If you see this point, okay, this point, fine. Okay, if you see this point is nearer to this cluster, right? This point is nearer to this cluster. So what I am going to do is, I will basically calculate the distance of each and every point in the second cluster from this point. Okay, I'll calculate the distance of each point from this point. Okay, is it clear? Fine. I'll take the summation and I'll take the average. So this is my B of I. Okay, this is my B of I. So this was A of I and this was B of I. Now for calculating the silhouette score, I'll basically tell B of I minus A of I divided by max of A of I comma B of I. Okay, I'll get the silhouette score. Now see, the more the silhouette score is towards 1, that is a well clustering. Okay, the more the silhouette score is towards -1, that's a bad clustering. Okay, always remember this. Okay, if my silhouette score is 1 or nearer to 1, then the clustering is done well. Okay, and if my silhouette score is towards -1, then that clustering is a bad cluster. Okay, you have to improve it. So this is how we calculate the silhouette score. Okay, this is how we calculate the Silhouette score. Okay. Until here, it's all clear. Fine. Great. Great. Okay. Now we will be discussing the practical implementation. Okay. Before this, I would just request you all to just revise all the machine learning algorithms. Okay, so we'll be like you know the entire procedure of the selection, right? So focus on that. Okay, and please attend the next session, which is the DB scan and the anomaly detection part also. Okay, so there you will understand how my there's how will you basically understand the clustering part which is used in the banking industry also. Okay, so anomaly detection is one of the concepts which is used in banking industry and the finance industry. Okay, anyways, let us come to the k-means. Fine, k-means practical implementation. I'll share the screen. K-means. Yeah, I hope it's visible. Yeah. Okay. Fine. So what I'm doing here first is I'm importing the basic libraries matplotlib, cbon. See, import cbon as SNS and sns.set. sns.set is basically the default palette of the cbon. This will basically beautify your graph. Okay, for your knowledge, and if you know, it's very good. Okay, then I'm importing make blobs. See, basically I'm not taking here the any data set for you. Okay, in the k-means part. Okay. We are basically making our random points. Okay, it's just the practical implementation, so I'm just going to teach you how the things basically work. Okay, so I'm making from sklearn the data sets, import make blobs. Make blobs basically initializes some random data points for you. Okay, the numpy pandas and import warnings. You're aware of this thing. Fine, so this is my line of code which will tell to make those points. I'm making 3 clusters. Fine, I'm taking 2 features x and y. Okay, and random set 23. Okay, note that here I'm taking x and y. Okay, so but as I told you, in unsupervised machine learning, what we do is we basically deal with the unlabeled data, right? We don't make any prediction or sort of thing. So just ignore the y part here. Okay, we have business with just this x part. Okay, fine. In your data sets, you can perform with the x part. Okay, then I'm performing x dot shape, so it's 1000, 2. Okay, then I'm plotting a scatter plot. So as you can see, these are my clusters. Okay, these are my clusters. Fine, these are my clusters. Now what will I do is, after this, from sklearn.model selection, I'll do the train test split. Okay, I'll do the train test split. Fine, this is clear. Okay, also guys, note one thing, that before doing the train test split, there's a concept of feature scaling also, right? Okay, how many of you know the concept of feature scaling? Okay, and rest all? Are you clear with the concept of feature scaling? Guys, response, or else I'll be in a confusion whether you guys know this thing or not, because this is something important, right? Okay, no. Others, Likit Kumaran. Okay. So what feature scaling is basically feature scaling is like you're scaling your all the features. Basically, let's say in one column I have my values as 1000, 2000, 3000 in thousands. Okay, and in the other feature I have my values in tens, like 1, 2, 3, 15, 16. So you can see there's a huge difference, right? So basically I'm scaling down my features. Okay, I'm scaling down my features to one range. Okay, this is important for a machine learning algorithm. Feature scaling is really important for a machine learning algorithm. Before training the model, you have to scale down your features to a particular set of values. Okay, in feature scaling, then you have two concepts: normalization and standardization. Okay, fine. Is this clear? Okay, so basically I'm scaling down my values in one range, and that is important. See, feature scaling is important in those algorithms. Okay, remember this: feature scaling is important in those algorithms where I have my distance parameter. Okay, now just recall the things. Where is my distance parameter? I have my distance parameter in k-means. I have my distance parameter in hierarchy testing. Now come to KNN. We have in KNN, right? Then we have the distance parameter even in linear regression. So these are all the algorithms where feature scaling is important. Okay, before training the model. Okay, is this clear? Where is it not important? Algorithms like decision trees, random forests, and everything. Okay, there you don't use any sort of things, right? You just do that, make those nodes and bagging and boosting and all this stuff. You'll be probably knowing it. Okay, so that's one of the reasons why people actually prefer decision trees and random forests. Okay, and the XGBoost algorithms. This is the reason to just and there's a concept of data imbalance also. Okay, so the algorithms like the decision trees, random forest, XGBoost, and everything. Okay, they work well with the imbalanced data sets also. Okay, and that is why you will notice that the accuracy of these algorithms are comparatively high to the other algorithms. Okay, generally. Fine. So this was a short note about features scaling. Okay. Okay. So what we done is we had divided our data into train set and test set. Okay. Now the main thing comes. We are importing k-means from sklearn.clusters. Okay. See, now first what we have to do is we have to take the value of k, right? So how will you take the value of k? From the elbow method. See, in Python coding, there's a manual procedure, that's the elbow method. There's one more procedure of calculating the k value that is from a library directly. I'll be showing you further. Okay. So from the elbow method, how we are finding the value of k? First, I'm initializing this empty list. Okay. Then I'm iterating from the values of 1 to 11. Okay. I'm initializing my n clusters as k, and see this init equal to k-means plus plus. Fine. Why am I doing this k-means plus plus? Init equal to k-means plus plus to escape from random initialization trap. Okay. Then I'm appending my list. Okay. Then when I execute this, and when I see my WCSS, now as you can see, WCSS value is reducing. Yeah, 34827. Then I have my 7935. Then I have 1119. Then I have 1140. So this is gradually decreasing. If it's okay, which is a good thing. Fine. After calculating this WCSS, what I'm doing is I'm plotting the elbow curve. Now see, this is my elbow curve. As you can see, the point of inflection. Okay, the point of inflection is after k equal to 3. Fine. After k equal to 3, this is getting stable, right? So my value of k will be over here 3. That's it. This is how I calculate the value of k. Okay, which is your number of clusters. Okay, this is a manual procedures. Fine. Again, this is not so complicated. You can just write this code down. Okay. Fine. Then I'm initializing this. Okay, n clusters equals to 3. Init equal to k-means plus plus. Fine. Then I'm fitting in the X train. Fine. I'm predicting the values. Okay. And then plotting the clusters. Okay. C equal to Y labels. Okay. Y labels. Fine. Y labels is my this thing. Okay. Now doing it on the train set. As you can see, there are 3 clusters. This black, pink, and this color, green color. Okay. I'm plotting my train set, and if you see, I'm plotting even my test set. So there are 3 clusters formed in train set as well as the test set. Okay, fine. Is everything clear until here? Yeah, great. Okay, I've done this. Now I will tell you a method of calculating the k value through a library. Okay, the library name, there's something called as knee locator. Okay, this is the code of knee locator. Okay, this is the 1-line code. So basically what I'm doing is I'm taking the range from 1 to 11. Okay, I'm initializing the WCSS, fine, and curve equal to convex, fine, curve equal to convex. So convex because my WCSS value is basically decreasing, right? WCSS value is decreasing, so I'm taking a convex curve, fine, and direction is decreasing, fine, and then KL dot elbow, and then I'm getting the value as 3. So the best value is 3. So this one liner code will help you to tell tell the value of K. Okay. Okay, so we have calculated the value of K, then we have fitted into a model, okay, and we have formed the clusters. Okay, just a second, I'm sorry. Yeah, we have formed the clusters. Okay, after this, I'll come to my performance metrics, which is the Siloid score. Fine. This is the code snippet of the Siloid score. Okay, I'll take the Siloid coefficients. Fine, and then I'll plot my Siloid coefficients. So this is my graph. Now, as you can see, for my number of clusters equal to 3, the Siloid score is the highest over here. It's peaking over here, right? Which says that yes, K is equal to 3 is right. So this says that yes, my clustering is good. If this curve would have come to 4, then my clustering would be incorrect or something like that. Okay, is it clear? This was how we calculated the Siloid score for K-means algorithm. Okay, clear until here? Yeah. And that's it. This is your K-means algorithm. Okay, guys, any doubt in K-means algorithm till now? Okay, I'll assume it. Yeah, it's all clear. Fine. I'll stop sharing this and let's come to hierarchical clustering. Fine. Now there's no change in the hierarchical clustering part. Okay, it's very simple. Hierarchical clustering. Yeah. Visible? Yes, is it? Yeah. Wait. Okay. So now let's come to hierarchical clustering. Again, I'm importing my data set. Let's consider I'm taking my iris data set. Fine. So I have. I hope you all know about the iris data set. We have basically 4 features: the sepal length, sepal width, petal length, and petal width. Fine. And then, as I told you, I'm scaling down my features. Right? I'm scaling down my features. I have used a standardization. Okay. And these are my values. Yeah. Okay, I'm taking this and I'm fitting it into my iris data. I'm naming is at X scaled. So I've got my X scaled values. Okay, I've got my X scaled values, and after this, I'm checking the shape of X scale, that is 150,4. Yeah. Okay. Now here's the thing. See, since I have 4 features, okay, there's something. PCA is principal component analysis. This basically what it does. Does it basically, right? So basically I cannot visualize on 2 dimensions. So that is 4D. That's why I'm taking n components equal to 2, right? And I'm fitting it, and then I'm plotting. I've got my data in 2 dimensions. If I would have just plotted like that, then it was very hard to visualize. Okay, PCA is even used to expression by Shiraz. Okay, so I've plotted my clusters, right? And now after the clusters, what I'm doing is I'm plotting my dendrograms. Now, if you go for manual coding for plotting the dendrograms in Python, it's very complex. So for that, we have in our SciPy library the scipy.cluster.hierarchy as SC. I'm importing it. This is the 1-line code for plotting your dendrograms. That's it. sc.linkage PCA scale. I have my scale values, right? And the PCA. Yeah. And method equal to what? What method equal to what does is this is basically telling that my distance parameter should be Euclidean. That's it. Okay. And this is how our dendrograms looks. Okay. These are my dendrograms. Now from sklearn.cluster import agglomerative clustering. Okay. And then n clusters equal to 2. Yeah. I can identify, if I draw a horizontal line over here, then I can say, these are the two clusters over here. Yeah, n clusters equal to 2, affinity is Euclidean, and linkage equal to odd. Fine, and then I am fitting this in the PCA scale. I've got my model. I'm checking the cluster labels. Yeah, and then I'm plotting the graph. As you can see, these are the black points. This is one cluster, and if it's hardly visible over here, you can see the second cluster also. Yeah, this is the second cluster, the creamish color, right? So this is my these are my two clusters formed. Fine. Then I'm going for the Siloid score, which is the performance metrics. Fine. This is the code. Yeah. And I'm plotting the Siloid score. So as you can see, for k equal to 2, the Siloid score is the highest. Fine. And this is the hierarchical clustering part. That's it. This is the Siloid score, and you're done. Okay. So is this clear? Yeah. Okay. So this was from my side, guys. We had discussed today about the introduction about the k-means algorithm, the unsupervised machine learning techniques, and then we had our k-means and the hierarchical. Okay. So tomorrow, please attend the sessions. Yeah, this is a request from my side, and then you will be having having your DB scan and the anomaly detection part, right? Shriyas, are you here?
Yeah, good. Yeah. Thank you
Yeah,
for
so
the
Sriraz
session.
will be taking your next session. Yeah.
Yeah, thank you for the session.
Also, yeah, I request everyone to just refer to books or some online materials also, right? So to gain some more knowledge, because unsupervised machine learning techniques, like if you come to the clustering part, you just don't have the hierarchical clustering, DB scan, and the k-means. You have even more algorithms, and who knows, they'll be more useful than the k-means and the other algorithms also, right? So just practice the codes, and I'll be uploading it in the classroom. Just practice the codes and refer to the online materials and papers or whatever you have, right? Yeah. So Sriraj, I think we're done.
Yeah, we are done.
Okay.
A
Thank you,
small
guys.
Yeah, small announcement, guys.
Yeah.
Tomorrow we will be having two sessions. One in the morning, 9:45 to 10:45, where I will be taking the PCA and the DB scan part. And in the afternoon session, we have Srijit, who will be taking a session on how to apply different algorithms on a particular data set. He will be taking up a stock data set, and he will be explaining how you can apply different algorithms, comparing the different algorithms and their accuracy and the stuff. So make sure you have attended the tomorrow's morning session and the afternoon session. And I think, how many of you have your resumes ready here? Like, how many of you have your resumes? Just raise your hands if you have a resume for you. So don't worry, guys. Like, we are planning to conduct a resume building session 2 on Monday. Please try to attend that itself. Before attending the resume session, I personally suggest you to work on some projects apart from the assignments or something which are given by our classroom in our bootcamp. You try to focus and try to implement the algorithms which you are learning on different data sets. Like, in the previous session, I have said you to explore the data sets and the stuff in Kaggle and GitHub, right? So try to explore different type of data sets and try to apply you learned algorithms there. Okay, guys, that's it for the session. Such anything left, or shall can we wrap up the session?
Uh, no, we can wind up the session.
Yeah,
So guys, practice the unsupervised part. Yeah. Just revise it and come, so it will be pretty much clear for you guys. Yeah. Okay. So thank you for attending the session, guys. Okay.